again, I would like to thank Vanderlei and Bill for really bringing such a great assembly in this incredible place. And now it went too fast, of course. Okay. And so I will give you some overview of some of the experiments that I've done in my previous life in Bordeaux with my former group there and also my former company Excel on sensors. So the sensors I will speak about are Matter wave interferometers, so in which we start with a bunch of laser-cooled atoms that we select in the proper state, and then we launch them in a series of 3 light pulses that will basically drive a spin echo experiment. So it's a Ramsey type of experiment that Bill described before with a pi pulse in between where we reverse both population and velocity. So the particularity here is that the manipulation creates a superposition of 2 states that will have different velocities because of the photon momentum. And thanks to this, these sensors can actually be inertial quantum sensors that will allow us to measure very precisely acceleration and rotation. So just very briefly to understand why we call these sensors inertial quantum sensors, we can just use Feynman path integral formalism in order to calculate the phase difference at the output of this interferometer. We basically have 2 classical trajectories, the 2 paths of the interferometer, and we can compute the integral of action along these 2 paths between the initial state at the input of the interferometer and the output state of this interferometer. And this integral of action will actually include any effect coming from acceleration, gravity, and rotation. But you also need to take into account the fact that the wave packets or the atoms will interact with light. And there is a second term coming into play when you calculate this phase difference. That's basically the phase which is exchanged between the wave packets when we make a change of state and a change of momentum during the manipulation and the laser itself. Actually, if you compute this configuration for a very simple case, which is I take my atoms, I let them fall down, and then I shine my light vertically, I found that because the atoms are following a geodetic trajectory, a trajectory which is affected by gravity, the integral of action drops to 0, and the only phase term that comes out of the interferometer basically comes from the interaction between the light and the atoms themselves. And it's as if basically the atoms were recording their position extremely precisely with respect to a very accurate reference, which in this case is the laser and defined by the laser wavelength itself. So the phase shift at the output of this interferometer, which in this case is in a gravimeter configuration, actually scales as the distance the atom travel between the first and the last pulse, so 1/2 of GT squared, divided by indeed the laser wavelength. So that's the phase term you can find here on the top right of the slide. And this is an accurate and an exact calculation at first order. I show you that some other term can appear if you make some more complex configuration. But this gives you first a very precise idea that the scale factor of the sensor is extremely well known. The only parameters that you need to know are the time, and we just heard that the time can be defined at 10 to the minus 21, and the laser wavelength, which is also like a metrologic definition. So we know the term that actually scale your sensitivity extremely precisely, which means that these sensors themselves can be accurate, and they can also be sensitive if you make a simple calculation. Let's say I have 1 second of interrogation time between the light pulses, and I use about 1 million atoms, so I have a signal-to-noise ratio of 1,000, not using any squeezing yet. The minimum acceleration I can detect with this gravimeter is of the order of 10 to the minus 10 meters per second squared. That's 11 orders of magnitude smaller than gravity. That's about 10,000 times smaller than the amplitude of fluctuations of the tides. And this corresponds to a change of height of less than a centimeter, because the gravity gradient is typically about 10 to the minus 9 meters per second square for about a centimeter of difference of height. So these gravimeters, we are actually building them today, and they are instruments that everybody can use, not even knowing or not even needing to know that they are basically using quantum mechanics to make the measurement. This is a picture of a commercial quantum gravimeter that is being sold. I think there is about 15 of such systems in the world, and this is the typical data that you record, that you see on the top of this slide. This data are fluctuating, of course. That's the tides, and there's this bit node between the tides induced by the sun and the tide induced by the moon. And the residual themselves are of the order of 10 to minus 9 G, so 1 microgal in the definition of geophysicists. What's important to know is in order to get this residual osmose flat, you need not only to take into account the tides, but also the fact that because of the tides, the crust is actually moving up and down. And this is what we call the ocean loading. And if you don't take this ocean loading, then you will have a residual. So it's really showing what is the accuracy and the precision of this gravimeter. So as I just said, these gravimeters are now used by non-quantum physicists, and they are basically starting to actually explore the capacity of these sensors. So this is one example where you put a gravimeter on the top of a place where below you have some water reservoir, and then you can just record how the soil is actually in time, because the gravimeter is very stable over a very long period of time. And this gives you an information, like when it starts raining, then the soil is charging, and then you have a strong gravity signal because water is very close to your gravimeter, and as soon as it starts dropping and diffusing slowly down to the reservoirs, then the gravitational signature will change. And these are the first signals that the geophysicists released from that, and they are still monitoring it. And what's very interesting is we're looking at prospects to really have networks of the sensors to really have monitoring in specific place that will allow us to get, or allow them basically, to get knowledge about the water cycle and how to actually let's say, manage our water resources using this knowledge. Another example, and this is a picture of a gravimeter which is not far from here, on the top of the Etna, and it's been sitting there for now almost 2 years, I think, where we used this gravimeter. Again, the geophysicists used this gravimeter to listen to the volcano, and recently they released a publication in which they were able to see, thanks to this the gravimetric signature, the movement of about 4,000 tons of magma about 3 kilometers below the surface, below the top of the volcano. So again, that gives you some ability to gain knowledge about what is the cycle, what's happening inside the volcano, and I don't see any easy way except by looking at gravity to actually record this. So this is giving you some, I mean, this is it's happening today. The real potential of these quantum sensors is starting to be exploited by the geophysicists for that purpose. On the other hand, we can think of really building, like exploiting this sensitivity to explore new areas of physics. And this is an example of a large-scale detector, which is currently being assembled 5 meters underground in France, in the southeast of France. This is basically a giant radiometer. So we have many different accelerometers that will record acceleration along the horizontal direction, and they are connected together with the same laser. And this could allow us, for instance, to observe and detect gravitational waves by just looking at the variation of the strain between the different atomic clouds at frequency much lower than the one accessible with the classical gravitational wave detectors, which are limited by seismic noise and gravitational noise. And there are also recently lots of studies and papers showing that this type of network of gravitational detectors can actually allow to rule out or rule in some models of coupling between light and dark matter, or between atoms and dark matter as well. And this is, of course, an ongoing project where we will certainly need to push the sensitivity of our sensors even beyond what we are able to do as of today. What I want to now tell you about is, let's say, more about some applications that are still promising, but still need a lot of development, and show that to get this development, we not only need to push the application and the engineering, but go back to understanding with like more depth how this quantum sensor works, basically. And one application which is very promising is position, navigation, and timing. The idea here is usually if you want to position yourself, the best way to do it is to use your sight. So either with your eyes, or even better by using beacons and GPS. But if you don't have access to this GPS or to these beacons, then you only rely on the knowledge of your internal motion, which we call inertial navigation. So in that case, you rely on knowing your attitude very precisely, and then also knowing your acceleration very precisely. And of course, in that case, you need to integrate acceleration twice, and any tiny error that you will have on the measurement, or any bias that you will not know or that will appear during the measurement, will actually lead to very strong errors. And as of today, the best inertial navigation system you can find, maybe not like top military grade, but they are limited to, let's say, precision of the order of a few hundreds of meters in about 1 hour, so which means that a good inertial navigation system in a plane today will not allow by itself to fly from New York or from Rome to the US without requiring any like site access or GPS recalibration. So in order to do this, of course, you need not only to measure acceleration along one axis, but the first thing is you really need to have access to the vector of acceleration, so the real let's say, magnitude and orientation of your acceleration vector. So for that, you need to build not only a single-axis accelerometer, but a three-axis accelerometer. And this is an example of the three-axis accelerometer we've been developing. We just use the fact that our quantum object is always the same. It's our cloud of cold atoms, and we just need to apply the configuration of laser the way we want in order to do the measurement. So in that case, what we do is we cool down our atoms with 6 beams, the same way you do classically for any type of cold atom experiments. And then we turn off 4 of the 6 beams, and 2 of them are used to make the interrogation along one single axis. So we do like one horizontal axis, the other horizontal one, then the vertical one, and we repeat the experiment at a cycle of about 10 points per second. And in that way, we are basically able to integrate and record the 3 axes of acceleration, or if we make the right combination, we have the magnitude, and then we have the 2 angles of orientation of the vector. Doing this, we can basically use this quantum measurement of acceleration to recalibrate the classical accelerometer that you usually have in a classical navigation, inertial navigation unit. And we basically use it as an internal GPS, like we recalibrate internally the drift that the classical system can have with the quantum measurement. And this is this Allen deviation that you see here. The purple curve is the result of the classical integration. If we put our system on a platform which is slowly moving and we are trying to record gravity in the vertical direction, of course, after a few seconds, the classical accelerometer starts to drift. This is why you have this purple curve which is going up. And and then the black curve, it's the hybridation, in which we basically remove the knowledge of the bias that we gain from the quantum accelerometer, from the classical accelerometer, as you see, after a certain while, which is just limited by our ability to make an accurate measurement because of the delay and the duty cycle of our quantum measurement. We start to integrate again and lower again our accuracy, which means that we've been basically compensating for the bias drift. Of course, this is only done in the lab, and we at the end we want to put it in a real environment. And in a real environment, you have vibrations, you have rotations, you can be in a plane like the one which is here, and you need to cope with that. So vibrations basically leads to the fact that if you do a measurement like it is done here in the plane which is vibrating, then you just have a random distribution of points. So that could like tell you that, okay, there's no way you can actually measure very precisely acceleration if you have a big noise. But the fact is we know everything about our quantum sensor. So we basically, if you look at the statistic of these points, you find that it's a very regular one, exactly the same that you would have if you would be able to retrieve basically the fringes of your interferometer. And because you know the scale factor very well, by just gaining knowledge about the noise, and this is done again by using a classical accelerometer to record the vibrations, then you can filter out the effect of the noise from on your quantum accelerometer. And in that case, it acts as a Vernier effect. The noise gives you a very large fluctuation of phase. You remove this, and then you're able to retrieve all the information from the quantum sensor. And this were the first measurement done live in a plane where we were basically able to record acceleration from the quantum sensor. Of course, this was nice, but we were not taking care of rotation and tilt. And rotation and tilt can actually, again, completely destroy your signal. Tilt, obviously, because then you don't know what you are measuring, and if you want to compensate for acceleration and you don't know what you are compensating, you're not able to do it. And rotation, because since the two wave packets travel at different velocities, then if you have a rotation, you have a differential Coriolis effect that actually is tearing apart the two trajectories. Your interferometer never closes, and if your interferometer does not close, then at some point you don't have any contrast anymore. And this is what we show here. This is an experiment done in the plane again for different temperatures. The Broglie wavelength, or in this case, the coherent length of your wave packet changes. And because of this, after a certain time, the spacing between the two trajectories is too large, and you cannot actually have any fringes anymore. So you need to cope with that. And in order to cope with that, again, we need the knowledge of our environment. So we record now not only the acceleration noise, but also the rotation and the tilt using a full navigation unit, like fiber optic gyros and mechanical accelerometers. And we feed back this information to our interferometer. So while we are basically performing the measurement on our quantum systems, we are putting some information about the noise and the rotation and the tilt. Doing this, the first thing you can do is we can actually record our interferometer signal with an arbitrary tilt and rotation. This is basically what you have here. So if you look on the left, you see a random distribution of points. This is just like all kind of measurements with tilt and rotation in a real, like in simulating a real environment. And of course, there is nothing you can really retrieve from that, except that we can exactly compute what is the phase shift and what are the different contributors for the phase shift. So this is the equation you see here. And in this equation, you have indeed acceleration along the different axes. You have also rotation, you have Coriolis acceleration, and you have also centrifugal force that appears to it. If you take all this into account, you are basically able to recompute the real phase out, and this is the signal that you see. So this is a fringe signal. Now this is the corrected phase. So this is just the term that I shown here. And this term actually includes some rotation terms. So which means that our accelerometer is not only an accelerometer, it's also a gyro. It's measuring rotation, tilt, and acceleration at the same time. And the only thing you need to do is now to be able to retrieve all the information in order not to lose anything. So this is what we've done here. And of course, there is still the loss of contrast because you see only a few fringes. So we can arbitrarily compensate for that by just like inversing the contrast loss. And this is what we see, but that's not helping us to make it work in a real environment. So in order to make this work in a real environment, we needed to compensate for the rotation. And again, the nice thing with this type of sensor is while the interferometers are free-flying, nothing happens. And we need only to compensate for the rotation when we interrogate the atoms with the light. So it's only for a fraction of milliseconds over a time of, in that case, 20 milliseconds of interrogation. So while we turn on the light, then we rotate the light a little bit in order to compensate from the rotation effect. And that works very well. You see that on the picture. We see again that we can reconstruct very nice fringes. And if you see at the contrast loss on the top picture, that you see a flat line on the top, this is basically making the measurement during rotation with this compensation. But of course, if you do that, you need to go back to what's happening to your matter wave, and you need to take into account all the phase term, and you add phase term now because not only do you have the phase term that come from the motion of the platform around the atoms, but also the motion of the mirror itself. But including that, then we are able to solve basically, and we are able now to derive a quantum sensor that is operating with like a rotation capacity between typically 200 radian per second and minus and plus 200 radian per second. So I want to stop there. I think it's only a few minutes, just to say that there are also other challenges that we are looking at. And one of the biggest one is the fact that there are lots of dead time in our measurement. We're solving it now by using this hybrid approach with like classical system. But of course, if we can go to continuous measurement or to quasi-continuous measurement, this will solve a lot of problems, and as well enhancing the signals using like squeezing, as mentioned before, is also one of the challenges we're looking at for this type of sensors. Thank you very much.